Hello and welcome to the Avid Technology Podcast with me, Ryan Morn. Today's podcast is in response to a question from a listener, so thank you very much for that. It's a really interesting topic, actually. So what they asked is, could we help them to understand the different terminology that's used in the electric vehicle world to describe electric motors? So they'd seen various different terms used like permanent magnet, induction, hybrid reluctance, switch reluctance, partial permanent magnet. And they wondered what they all mean. And actually, they also were wondering what's the best kind of motor. So let's first, I think it probably is helpful to start with the basics. And apologies if you already know this, you can fast forward. But basically, all electric motors work on the same principle. And we can see that if we're playing with magnets. So, we all know if you're playing with magnets, if you put a north and south together on two magnets, they attract each other. But if you put a north and north together, they repel each other. And you can play games pushing magnets along the tabletop, which is quite fun. In an electric motor, we're creating that electromagnetic reaction force in the air gap between the rotor and the stator. So we need two magnetic fields for the motor to work, one in the rotor and one in the stator. And in fact, actually, we have many magnetic poles inside the motor. So we're creating many simultaneous reactions. In order to create the movement, we've got to switch these magnetic fields on and off at quite a high frequency. This creates the electromotive force, or EMF, and it makes the motor spin, and it creates our torque. The torque we can create in the motor is a direct function of this magnetic reaction in the air gap. More magnetic field strength, more force, more torque. So how do we create these magnetic fields? Well, the easy part is the motor stator. And the stator is so called because it's stationary, it doesn't move. So that would tend to be fixed to the housing of the motor. The stator is an array of small electromagnets. And these are created, so the electromagnets are created by wrapping conducting wire, normally copper, around a specially shaped tooth made from some sort of ferrous material, so steel basically, iron. So we wrap the copper wire around the steel, which is in a special shape, and when we pass an electric current through it, that creates a magnet on the tooth of the stator there. So if you look at our YouTube channel, you can find a video on that which shows lots of different types of motor and what the motors and stators look like. And we'll put a link to that below in the show notes. So that's the stator. It's your stationary electromagnet. Next, it's the rotor. So how do we make a magnetic field in the rotor? And there are various different ways to do this that give the motors their names. In low-tech electric motors, these are mechanically commutated using carbon brushes. So the carbon brushes run against a commutation ring as the motor is rotated, and it passes electric current from the stationary side into the rotating side. And that current goes into a wire that's wrapped around a special shape on the rotor, and that creates a magnetic field on the rotor. And then the commutation ring that's spinning, as it goes over the brush, basically it's flipping around that magnetic field on the rotor. So it's moving that around as it needs to. The problem with brushed motors, so quite old-fashioned, is they're not very efficient and the brushes wear out. And if you ever used a kind of hand power tool a bit too aggressively, you get that kind of smell of burning carbon coming out the back of it. That's the brushes being worn away in the back of your tool. Or sometimes you can see little sparks if you look in the back of a hairdryer or something like that. So not very good motors. They are used in lots of applications, quite common, but really, no good for an electric vehicle, which needs a high efficiency and needs the motors to last pretty much forever. So not brushless motors are not suitable. But then we have what's called electronically commutated, or sometimes EC motors. So there's no brushes here, so brushless motors. The most common kind of motor, not necessarily in electric vehicles, but just globally, the most common kind of motor is an induction motor. So an induction motor basically has a rotor, sometimes called a squirrel cage design, because it looks like a cage that you kept squirrels in. I'm not sure who keeps squirrels anymore, but it looks like a cage. They're copper bars. They tend to be sunk into an aluminium core. So you have these copper bars, and they basically act like the coils in a transformer. So the magnetic flux in the stator creates a lagging magnetic field in the rotor, and we get the reaction between the two magnetic fields. We get EMF. So induction motors, I said they were really common at the start, but not necessarily in electric vehicles. So they are very, very common in industrial applications. The principles of induction motors have been around since like late 1800s. Galileo Ferraris was the first. I think Nikola Tesla is fair to say he probably perfected the design. He secured a number of patents, which were then licensed to some other pretty big players, GE, Westinghouse, people like that. And, induction motors are not very common for EVs, with a bit of a caveat here. So they are used by Tesla. The Roadster and the Model S do have induction motors in them, but they're not really very widely used elsewhere. And that's because they're relatively heavy, and they're not as good as some other motor types with low-speed torque. So the motor ends up being oversized to do the job that you want it to do. But a really good advantage of an induction motor is that you can control the field strength of the motor rotor. So if you can sacrifice a bit of mass and a bit of volume, induction motors are pretty low cost. They don't rely on rare earth magnets, so they're not a bad motor to use, but they're not that common in high performance applications other than at Tesla. So the next type of motor next up is what we call permanent magnet motors. So in this kind of motor, as the name implies, we embed magnets into the rotor to create a set of permanent magnetic poles. So PM synchronous motors have also been around for a very long time. I have a feeling that PM motors existed first. I'm not quite sure on this. I'll have to go and look at that. Pretty sure PM motors existed first. We make a really strong magnetic field with special magnets now that use rare earth alloying elements to improve their performance. And these magnets can be arranged in one of two ways. So they're either on the surface of the rotor, and these are called surface permanent magnet motors, so SPM, if you see that, or they can be embedded into the rotor, and that's known as an interior permanent magnet motor, or IPM. SPM motors are pretty simple to understand. IPM can be a little bit more complex. So on an IPM motor, the rotor is going to be made of a ferrous material, so typically sheets of lamination steel, again, very thin sheets of steel that are pressed with a particular pattern in them. The magnets are going to be inserted into that, and basically you use the steel and the little sort of things that you punch into it as a flux guide. So that guides the magnetic flux to the surface of the rotor. And what it means is you can create a stronger magnetic flux at the surface than you could with just with a surface permanent magnet. So you can get more kind of active magnet in basically to couple to get higher flux concentration at the surface, and obviously that means more torque. So that's the first kind of reason why you would do IPM in a motor, to get more magnet per area of rotor surface in. The other thing that's quite interesting that you can do, you then have some quite big areas of iron in between the magnets, and we can generate a secondary magnetic field with what's called the reluctance effect in the motor. You see that a typical rotor, the magnets are sort of organized normally in a V configuration. You might have a stack of those Vs, so two Vs, one on top of the other, or a V with a magnet in the middle of it, so 3 magnets on each kind of piece of the rotor. But then you've got other areas which effectively don't have magnetic flux concentrated in them. But this thing called magnetic reluctance then comes into play. And basically what that is, we can generate a magnetic field in the rotor by using stator current. By clever control of the motor, we can generate some reluctance torque. So then the amount of torque you can get out of the motor then is a function of the amount of permanent magnets that we've got and the amount of reluctance torque that we can generate in the rotor. So that has a pretty big advantage. And basically, the reluctance torque, the benefit of that is you can turn it on and you can turn it off. That means that you can alter the magnetic field strength of the rotor. And that's quite important in an EV traction application where you've got a very wide operating speed and load distribution. So, in some applications, like passenger vehicles, you're not always full throttle, they're not always fully loaded, quite often tootling around at light loads and varying different speed conditions. So you don't always want the full performance of the motor, but with a conventional surface permanent magnet motor, you can't do anything about it. The magnets are there all the time. You have to use power to do something called field weakening, which really damages your efficiency. But with an Ipm motor, you can basically control it in such a way that you effectively turn off the reluctance portion of the motor if you don't need it. So it's quite good in that respect. It allows you to do very strong field weakening without putting that much current in. So you basically end up with a motor that's very efficient over a wide speed range. So it does sacrifice peak efficiency typically, but its overall cycle efficiency will be better than a plain old surface motor. So that fact that you can control that, you can then effectively, because you've got the reluctance torque, you can use less permanent magnet material relatively to the amount of torque you're getting out of the motor. So you can have very nice optimized motors. And I think basically for that reason, Ipm motors have become by far the most common motors in EV powertrain, because they're improved power density compared to induction machines, and the ability to control this reluctance torque, which improves driving cycle efficiency. When Tesla talk about a hybrid reluctance motor or a partial permanent magnet motor, this is what they mean. And it's basically the same motor technology and topology as can be found in a Leaf or a Bolt or a Zoe. So all, pretty much any EV now coming on the market, they're all Ipm motors for this reason, because you get this sort of nice balanced optimization of the motor. Now you can take the Ipm concept to the next level, and you can have a fully switched reluctance motor. So in this type of motor, there's no permanent magnets in the rotor anymore. We're just using that magnetic reluctance effect to generate the magnetic field in the rotor. In theory, this kind of machine can be really cheap because it takes away the need for rare earth magnets. But in practice, actually, there's some pretty big trade-offs there in terms of the power density, low power density, high torque ripple, difficult to control, along with actually there's some pretty big tolerancing issues in the manufacture of the rotor in particular, and that's limited the uptake of this kind of machine. But if you can make a sacrifice in terms of power density, and you don't mind the torque ripple so much, then switch reluctance could be good. But I don't know, I could be wrong, but I don't know of any on-highway traction applications that use switch reluctance. I know some off-highway applications, so like diggers and bulldozers and this kind of thing where they're using switch reluctance, but I don't know any on-highway applications where they use switch reluctance machines for their traction. Maybe if rare earth prices shoot up, or there's some sort of problem there, that might increase the use of reluctance machines. I think the magnets and the materials being reduced quite significantly in good Ipm motors these days, so not sure. The big thing though with electric motors is its optimization. So basically people are working really hard all the time optimizing motor designs and trying to get higher power densities for lighter, more compact motors. That means looking very closely at the cooling on the motor and the thermal management within the motor, because basically the main challenge with an electric motor is managing the heat that's produced inside the motor because of the ohmic losses by the current passing through the wire, and ion losses caused by the electric and magnetic fields inside the rotor. And that all generates heat, and you have to deal with the heat and get it out of the motor. And if you've got a big lumpy motor that's not very power dense, the housing and the components in the motor just absorb all of that, and it's not a problem. But the EV traction motor, you're pushing power density all the time. You're trying to get rid of materials wherever possible, and that means dealing with the heat inside the motor is a much, much bigger challenge. So there's lots to do with thermal management, cooling in the rotors, cooling of the stators, good filling inside the stator windings with thermally conductive encapsulation materials, etc., etc. It's a huge kind of field. There's also a big thing in terms of cost, and I think this has changed slightly over the last few years in that, maybe 5 or 6 years ago, people would have said, and this is actually probably what led Tesla to fit induction motors, right, the cost of the motor is the number one thing, so we want a cheap motor. But now, actually, I think what people recognize is that the cheapest motor doesn't necessarily give you the best EV, and even the lowest cost EV, and depending on obviously how you look at the cost of the electric vehicle. And so what I mean by that is people have recognized that it's worth investing in the powertrain because essentially the cost of the battery blows everything else to bits. So the most important thing to do on your EV is have a really, really efficient powertrain. And that means lightweight, because the heavier the powertrain is, the more energy you need to push it around. And that means very efficient across the operating cycle. So you can maximize the range that you can get out of the vehicle for a given amount of battery, because the battery is really, really expensive. And the thing that's going to sell your EV is the battery range. And the thing that's going to drive the cost on your EV is the battery cost. So you can add a few dollars of cost to the motor to improve system efficiency and take some weight out, because it's going to give you a better performance and a better package value proposition overall. So people have become really savvy to that. So that means that rather than working on the cheapest motor, I think there's a very high level of awareness now in terms of the value proposition. So cost optimization is still really important, but it's cost optimization with that performance in mind. So that's looking at things like the winding techniques. So there's a big area there. Things like hairpin windings, square bar, or concentrated windings. And the purpose of these two methods is to improve the copper fill factor in the motor and basically reduce the winding overhang. So that's the bit of copper that's basically not used. It's not within the main body of the stator. It's not doing a useful job. It's just going from one part of the stator to the other. And then if you look at some electric motors, there's an awful lot of overhang copper there. So effectively wasted copper, which is extra cost. So techniques that can minimize the cost but optimize the performance, not necessarily the cheapest, but the best performing, best cost compromise for the device. That's really where all the activity is at in order to try and get the best out of your electric vehicle. There are other kinds of motors on the market. So all of the ones I've described are radial flux motors. You also have axial flux motors. So axial flux is not so common at the moment in electric vehicle traction applications. There are applications that use it. Avid sells axial flux motors. So things like buses and trucks and some high-performance vehicles are using axial flux motors now. There's some supercars and hypercars out there that have axial flux machines in. So axial flux is coming. Basically, axial flux machines are a surface permanent magnet. There are some axial fluxes coming that have use a bit of reluctance effect, but you don't tend to get very much reluctance effect. You do get very good magnetic surface area and very good use of the magnets within the motor. So axial flux is going to come through as well, but still a lot of applications, particularly the volume applications, radial flux motors are going to be the ultimate solution. And the direction of travel in terms of technology development is all around cost optimization on high performance radial flux motors. So it's not necessarily going to be the absolute highest performance motor that wins, the one that has the best balance of cost, weight, efficiency. And then when we translate that back into the whole vehicle cost, that's then going to really drive the value proposition for the vehicle. So I hope that I haven't just completely rambled on there for 20 minutes or so. And I have actually managed to explain some of these different motor types that are out there and the different terminologies that are being used, your IPMs from your SPMs and your partial magnets, and essentially basically all boils down to three types of motors that you will see in an EV driveline. Induction motors, becoming less common, were used by Tesla, surface permanent magnet motors, and IPM partial reluctance motors. So they're the kind of the ones that you will see. By quite a long way now, IPM motors are the most popular because of the benefits they bring in terms of the ability to optimize the amount of magnet, generate reluctance magnetic effect, and have very high power densities, torque densities in those motors relative to the other radial flux technologies. Not quite as good as an axial flux motor for a torque density point of view, but very, very good motors nonetheless. So that's all we've got time for today. I hope that's been useful, and I look forward to talking to you again soon. Don't forget to subscribe to our channel. Leave us a rating or comment if you're listening to this on YouTube. Your feedback really, really is valuable to us. Also, if you've got a topic that you're interested in that you'd like to hear us talk about, or someone you'd like to hear us talk to, don't be shy, send those in. We are covering more and more listeners' questions in the future. We're starting to see quite a few of those come in on some really interesting topics, so really looking forward to bringing some of those to you. We've also got some fantastic interviews lined up with some really, really knowledgeable people, so they're going to be interesting. I can't wait to get those podcasts out. So that's all from me for today. Thanks for listening, and I look forward to speaking to you again soon.